So in conclusion, there are two parts to the fundamental theorem of calculus. Depending on the book, the order will change. We have part 1. If a function f of x is continuous at every point on AB, and large f of x is the antiderivative of f of x, then this is the evaluation part. So we can find the area under the curve. We can evaluate the definite interval by integrating and evaluating, and that's what we've been doing for a while. And then we learned a second part to the fundamental theorem of calculus. Okay, so the second part, if our function is continuous at every point on AB, then if our function is the integral from a to x, ft dt, it has a derivative at every point on AB, and the derivative and the integral are inverse operations. In other words, when we take the derivative and then we integrate, we get back to the original function minus our constant, which gets lost. Okay? And so here, if we are taking the derivative and then integrating, those processes are going to cancel each other out. However, since we're integrating to a variable, that variable will replace the variable in the integral. Right? So it's going to cancel each other out, but change our integral, our variable here in our function. The constant, however, because we took the derivative, will be lost. Right? When we take a derivative, we lose the constant. Right? Seems really easy, that second part there. However, beware. Right? So when the derivative of the bounds is anything other than x, you need to multiply our function by the derivative. So here we have an example, right? And we want to take the derivative of the integral of 2t dt from 3 to x cubed. Right? That x cubed we have to use. Right? We have to take, it's a chain rule, we have to take the derivative of x cubed and multiply it. Right? We can't just substitute that in because it's not just an x. Right? Just like when we take the derivative of something raised to a power, if it's inside parentheses, if it's inside another operation, right? We have to take the derivative of that inside part. Well, that's the inside part. Right? So here we would replace the t with x cubed, but then we have to multiply by the derivative of x cubed, which is 3x squared, and gives us 6x to the 5th. Just to prove this is so, I did it the long way without using the fundamental theorem of calculus. Okay, so I integrated and then I evaluated. Right, so if I integrate 2t dt, I get t squared. I get 2t squared divided by 2, so that's just t squared. And we're evaluating that from x cubed to 3. I mean, from 3 to x cubed. I plug in the x cubed for the t, and so now I have x cubed squared, which would give me x to the 6th, and I have minus 3 squared, or 9, right? Because I have to plug in both. Now if I take the derivative, I get 6x to the 5th, which is exactly what we got using the fundamental theorem of calculus. Right? So here it shows you how the derivative and the integral are inverse operations. The only thing that gets lost is the constant, because the derivative of a constant is 0. We can't get that back again. So the FTC is unquestionably the most important theorem in calculus. Indeed, it ranks as one of the great accomplishments of humanity. Hope you've enjoyed this series of podcasts. Thanks for watching. Bye.